Assalamu alaikum. My name is Wasim Gul and I will be presenting CPU virtualization. So CPU virtualization, we can also call it the invisible orchestrator. So here we explore the foundational concepts of CPU virtualization, its necessity in modern computing and the core mechanism that enables it. So there are three architectural stages. The first one is the vanishing physical border. The second one is the conundrum of shared resources, and the third one is like why it matters, efficiency and consolidation. So in the core mechanism, we study the trap and emulate mechanism, which is like privileged and non-privileged instructions, which CPUs categorize instructions non-privileged for user applications and privileged for sensitive kernel operations that directly interact with hardware. The second one is the trap mechanism. When a guest OS attempts to execute a privileged instruction, the CPU intercepts, like traps it with redirecting control flow to the hypervisor. And the emulate response, the hypervisor then simulates the expected outcome of the privileged command for the guest, maintaining the illusion that the guest OS has direct hardware access. So this trap and emulate model is the fundamental to ensuring security and isolation. Like it also prevents a virtual machine from directly interfering with another or the underlying hardware. In the protection rings, we call it the OS perspective, from the in which we study the ring deprivileging. Traditionally, OS kernels operate in ring 0, uh, ring or ring O, and the highest privilege, which is also the highest privilege level. Like you can see in the diagram, in a virtualized environment, the guest OS is deprivileged, often running in the ring 1 or non-root mode, and the hypervisor's throne, which the hypervisor assumes the control of ring 0 to establishing itself as the ultimate authority and mediator of hardware access. The final is like why it matters. So this hierarchical privileged structure allows the hypervisor to manage resources and isolate guests without their direct awareness, forming the core of virtualization security. Now the next topic will be presenting Sohaib Amir.
My name is Amir, and uh, now I will present after Wasim architectural approaches and real world deployments. Essentially, we are trying to trick an operating system into thinking that it has total control over the hardware, even though it's actually sharing that hardware with dozens of neighbors. There are three main ways we are figured: binary translation versus para-virtualization. Back before CPU were designed with visualization in mind, we had two clever but very different workarounds. Let's discuss about binary translation. We say that it is an invisible translator. Think of a binary translation like a real-time translator of United Nations Summit. The guest OS, like Windows, tries to execute a privileged instruction. It's dangerous. Yeah, basically something that could crash the whole physical server. The hypervisor that Wasim has discussed before, the hypervisor catches it mid-air, rewrites it into something safe, and let's run it. The big wins. The approach requires no modification to guest operating system, and we do not have to change a single line of code in the guest OS because it just works. The catch, it slows. It is like trying to have a conversation where every third word has to be looked in up in the dictionary. Now let me discuss about para visualization. Now para visualization takes different approach. We actually go into the guest OS kernel visualization aware. Actually, when we tell the OS, hey, you aren't the boss here. When you need to do something big, don't try to do it yourself. Just ask the hypervisor. Hypercalls and the result. Hypercalls are the trap that OS makes. Basically, it is a polite request, and the result is a closed, like old versions of Windows, where you can't touch the source code. Direct request to the hypervisor for improved efficiency. Now I will discuss about performance implications. Performance implications are like hardware assisted virtualization. Uh, Para-virtualization generally offers significantly higher performance by implementing the overhead of repeat and traps, but it mandates cooperation from the guest kernel. Now I will discuss about hardware assisted virtualization like Intel VTX and AMD V. Today we do not have to choose between the two as much because Intel VTX and AMD V built virtualization directly into the silicon. Uh, Hardware support, VMCs, virtual machines, control structure, and why it matters. Let me start about offloading to silicon. Instead of the big software doing the heavy lifting, the CPU has the virtualization mode that we see in our Windows, and the VMCs are the safe game files like that. This is a secret source code, and the virtualization machine control structure is hardware managed data structure. It stores the entire state of a guest CPU. When you switch from VM-A to VM-B, the hardware swaps the structures almost instantly. Now, why it matters? As you know that it makes virtualization feel almost native. We are talking near 100% physical speeds. Now, implementation examples are we have covered two: VM, where most commonly used, and KVM. To wrap up, let's me look how this looks in a data center. Uh, as you see in industry, VM, where the specialist is a type 1 bare metal hypervisor. It does not sit on top of Windows or Linux. It is the OS because its purpose is to build solely and to run VMs. It's incredibly lean and stable. This is the gold standard of for big enterprises data centers. KVM, as the name suggests, kernel-based virtual machines, has the virtual machine. This is a bit genius more. It turns the Linux kernel itself into hypervisor. KVM is a virtual machine. It is just a process of support of by Linux. This means that KVM gets all the security and hardware support of Linux for free. And now let me discuss the impact on cloud computing. Hmm. If you ever used AWS or a Google Cloud, for example, in AWS there are multiple types of visual cloud computing uh, that you are likely running on KVM. It's the engine that powers the modern cloud because it is open source and incredibly flexible. So whether it's the software trick or hardware assisted, brute force visualization is always allows on one server to do the work of 50. Thanks for listening. Now Moise will present rest of the presentation.
I'm going to talk about how the cloud actually works behind the scenes. It's basically a story about how we try to make computers fast, but also keep them safe and private. So, there are different challenges, trends, and the future of the virtualization. First of all, I will discuss about the tax of virtualization. So when we run a virtual machine, it's not talking directly to the computer hardware. It has to go through a middleman called the hypersupervisor. So every time the VM wants to do something, it has to stop and ask the middleman for permission. We call this VM exit. For example, think of it like a tax. It costs a little bit of speed every time. The biggest challenge for engineers is to trying to keep things fast while making sure one VM does not mess with another one. After that, there is a challenge which is known as CPU scheduling and steal time. There are total three categories in which the first one is two-level scheduling, then CPU steal time, and okay. First of all, I would discuss two-level scheduling. In this, um, there is a big problem called steal time. Imagine you are at a restaurant and you are ready to order, but the waiter is busy helping three other tables. You are just sitting there and waiting. That's exactly what steal time is. Like your virtual machine is ready to work, but the actual physical CPU is busy with someone else VM. If the steal time is high, your app is going to be slow and laggy, and there is not much you can do but you wait. Why it matters? High steal time directly correlates with the unpredictable and degraded application performance, and a critical concern for workloads in shared cloud environments, which are guest OS schedule, vCPU queue, hypervisor dispatch, physical CPU, and steal time delay. After that, there are some current trends which are confidential computing, related to the confidential computing, which includes secure enclaves, data protection, and zero trust future. So, first of all, I will discuss about the secure enclaves. Um, Confidential computing, which is usually the people who own the cloud servers, could technically see your data if they wanted to. But the new CPUs from Intel and AMD have these secure enclaves. Like for example, if I talk about the real world scenario, it's like a digital vault inside of the chip. Even the person who owns the server cannot see what inside. This is zero trust model, and it means we can put super private stuff like bank info in the cloud, and now it's 100% safe. So finally, coming to the summary and the conclusion, first of all, I would like to discuss about the evolution of the virtualization, then cloud's silent engine, and then the future is hardware centric. So to wrap up, virtualization has changed a lot. It is used to be a clunky software trick, but now it's the silent engine of the internet. In the future, all this virtual stuff is moving directly into the hardware. This means the cloud is only going to do faster, more secure, and more powerful from here. And the future is hardware centric. As CPU continue to scale in core count and complexity, the core logic of the virtualization is being pushed deeper and deeper into the hardware, promising even greater efficiency and security. Thank you for listening.